Hey everybody, it's Mrs. Dr. B. We are on week 2 of kinetic molecular theory. Kinetic molecular theory takes and really stresses and focuses on the role that energy plays in changes in matter. Now, this does not have to be chemical changes, but it can be also physical changes. The first topic of this week, which is this particular video, has to do with the top bullets on our checklist. We are looking at heat and specific heat. We're going to be doing some math with regard to this. Then you will have a second video later in the week. I would assume that will be on your block day, and that's going to be on heat transfer, just spending a little bit more specific time with exothermic and endothermic. Please remember to check your checklist. Stay on top of it. Make sure that as we are moving through the material that in fact you are moving with us. Okay, so let's get started. We are talking today about specific heat. Really and truly, when we talk about specific heat, we're going to figure out why some things get hotter faster than others. It's an intensive property that just basically says, it measures, describes the amount of heat energy required to raise the temperature of a substance, whatever that substance might be, per unit mass. It is a physical property, and because it is defined by the identity of the material, not by how much material there is, it is an intensive property. What this means is that you can find specific heat values for materials in data tables. And it doesn't matter whether you got a ton of something or you have a few drops of it. The specific heat capacity, the amount of energy it takes to raise or lower the temperature of a material per gram, generally, sometimes per kilogram, is known as the specific heat capacity. Okay, so you will see sometimes people refer to specific heat capacity using a lowercase s. Sometimes it is a c. I cannot explain why they use different numbers or letters, but they do. All right, so here again is the definition, the amount of heat. Now, heat is generally measured in joules, and you're going to say to raise 1 gram of a substance, 1 degree or 1 Kelvin. So you'll see the units out in the middle, joules, divided by 1 gram times Kelvin. Once in a while, people will use calories instead of joules, and you can see how the formula changes. Instead of joules, it just says calories. Sometimes people refer to specific heat capacity in kilograms instead of grams. So if you go back to your original one, instead of 1 gram, you see kilograms. Other times you will see that degrees Celsius will be used instead of Kelvin. And so it would be joules per gram degree Celsius. The only reason why Celsius can be used is because the size of 1 degree Celsius is the same as the size of 1 Kelvin. And so when you're looking at differences, it becomes interchangeable. All right, the second term for this week, or this unit is, or this video, I should say, is heat capacity. It's related to specific heat, but it doesn't have the reference to mass. In other words, it's an extensive property, because with heat capacity, it depends on how much material you're trying to heat or cool. It's a ratio, and if you'll read through that, it says how much energy was, amount of energy was transferred to a material or from a material, and how much the temperature of the material changed. So if you look at the formula in the middle, Q represents the energy. C, which is an uppercase C, is heat capacity, and delta T is a change in temperature. So in this particular case, C has the mass in it, because it depends on how much there is. All right, so let me just show you the formula for heat capacity. It can be calculated by simply taking the specific heat by the mass. In other words, if I have a specific heat of 2 and I have 4 grams, the heat capacity is going to be 8. It's that simple, right? It's going to be that simple. Okay, remember specific heat itself, the S, is per unit mass, so its value does not change. Read this stuff in bold there, guys, because that's real important for you as you move forward. The specific heat of a gallon of water is the same as the specific heat of a drop of water. However, the heat capacity of the gallon of water is a lot more than the drop of water. All right, so there are lots of tables out there. This is the one I'm going to share with you, and I'm just going to put it over here also to the side. And you will see that there's a number of specific heat values that we're going to look at. I would suggest you very definitely keep this resource, specific heat resource, with you, because you're going to be working some problems. And you can see there's two columns. One is the typical way of reporting it, which is joules per gram Celsius. The other one is in calories. Okay, so what this should help you see is that water at the very bottom of the list has a heat capacity of 4.186 joules. That means it takes over 4 joules of energy. And I know you don't want to know what a joule is, but it takes over 4 of them to raise a gram of water 1 degree. That's what it says. It takes more than 4 joules of energy to raise 1 gram of water 1 degree. That's a really large specific heat. It's why water is really good at regulating temperatures, why the beach water doesn't warm up as quickly as the air does. It's why your pool water doesn't cool down as quickly in the fall as the air does. In contrast to that, you'll see that the specific heat capacity of copper is 0.39. It's really easy to heat up copper. It's even easier, look at gold at 1.29, to heat up gold. It's really easy to heat up gold. Lead is easy to heat up, and that's really good because the folks who solder, who use lead to solder, they need to be able to get it to a molten state. Well, what does that take? It takes heat. And you got to get to that boiling point or that melting point. And so you've got to make sure, see how much it takes to do that. All right. On a per gram basis, you can see, copper heats up. When you look at the numbers there, copper heats up almost 10 times faster than water does. Okay. Big important news flash here. Specific heat and heat capacity have nothing to do with energy used during phase changes. The heat of fusion, the heat of vaporization, has nothing to do with specific heat. Specific heat has nothing to do with really and truly the heating and cooling curves. It really doesn't. Now, what it does do, something that has a very low specific heat capacity, the sloped lines on the heating curve are going to be steeper. Why? Because it doesn't take as much energy to make it happen. But the phase change, those flat lines are not going to be affected by specific heat and heat capacity. And the reason why is because when we are breaking things up, we're breaking the intermolecular attractive forces, we are not increasing the temperature. Okay, so what I want to do now is I'm going to actually work 2 problems for you. And once I finish those, then I'm going to give you another class assignment where you're going to work them on your own. So let me get set up. Okay, so folks, here's the first practice problem. You'll see it's in both places. It's both on the left and on the right. I'm going to work the problem on the whiteboard on right here where my hands you're seeing. The problem reads, the specific heat of ethanol is 2.46, I can't read, joules per gram degrees. So this is going to be your C for the problem. Find the heat required. Heat is going to be the Q. To raise the temperature of 193 grams, there's your M. And then you have to raise the temperature from 19 to 35. So delta T is going to be equal to the final temperature of 35 minus the beginning temperature of 19. And this is degrees C, which is, of course, 16 degrees C. So this is delta T. So we've now identified all of our parts. So all we have to do is put them into an equation. And the equation reads Q, which is what we're trying to find. This is going to be in joules. I'll prove it to you in a minute. Is equal to 193 grams times 2.46 joules per gram degrees Celsius. This is the units on the bottom, times 16 degrees C. All right, that's the problem. We identified everything first. It's really important that you do this as you're starting new problems. Now let's look. C cancels because it's on the top and the bottom. Grams cancels because it's on the top and the bottom. The only thing you're left with is joules, which is in fact the unit for the Q. So now all you have to be able to do, guys, is do the multiplication. All right, so let's do this multiplication. We are going to take 193 times 2.46 times 16, and we are going to get this number. We're going to get 7,596.48 joules. All right, we have 3 sig figs here. We basically have 2 sig figs with this math here and 3 here. So your answer could be this number that you're given. You would be more than happy. I'd be more than happy to have you just take it and not worry with the decimal places at all. Yes, that is 4 sig figs. Or you could get credit for it for just writing 7,600 joules. So that would be your answer to problem number 1. Hi guys. So we have a second practice problem. This is a different type. The first time we were actually using the equation as written, Q equals mc delta T. In this particular case, what we are looking for is the C. So we have to rearrange the equation. Now I'm not going to do that for you. I'm just going to do it in the problem because that's the way I do it. If you have to rearrange the equation to solve for C, please do so, but you're going to see me do it. All right, so what do we have? We have a 120 gram sample. There's your M. All right, and we're going to say that it absorbs 9,612 joules of energy. There is Q. The temperature increases from 25 to 115 degrees C, so that means our delta temperature is going to be equal to 115 minus 25 degrees C, which means we're going to have delta T equal to 90 degrees C. So we've identified our Q, we've identified our M, and we've identified our delta T. All we have to do is solve for C. Now, personally, this is the way I do it. I'm just going to fill it in. Q is equal to, look at it, 9,612 joules. I've used that piece of information now, is equal to M, 120 grams, times C, which I don't know, times delta T, which is 90 degrees C. So the way I do this, because I'm not worried about rewriting it, I'm going to try to isolate C. All right, let me put that in a different color. I'm going to isolate C. So how do I isolate C? Well, the first thing I'm going to do is I'm going to take both sides and I'm going to divide it by 120 grams. When I do that here and I do this here, guess what? It cancels there. All right? I still have C and 90. What do I need to do next? Well, I need to get rid of the 90. So what am I going to do? I'm going to divide both sides by 90 degrees C. And what you're going to notice is that the only units I'm going to have left, because watch this happen, is going to be joules per gram Celsius, which, guys, believe it or not, is the units joules per grams degree Celsius is the units of C. So we've set this up correctly. Now all we have to do is the math. All right, so let's do the math, guys. I'm going to take 9,612 and I'm going to divide it by 120, and I'm also going to divide it by 90. And my number is going to be 0.89, oops, that's supposed to be a 9, it's not supposed to be, sorry. Let me do this again, 0.89 joules per gram degree Celsius. 0.89 grams degrees Celsius. So guess what? It says it's aluminum. We actually had the information here, and if we look here, we can see that aluminum right there, it's a little bit different, is 0.902. Not far off. Okay? Not far off. If you did not have this list, you'd be able to check it. Or if you have it, you can check it. All right. So that's the second one. Next are the ones that are going to be assigned to you. So hang on just a second. Let me get that set up. All right. So this video closes out with this. You have these three problems to work. These you're doing on your own. So the first one, number 3, is the same as the second problem I worked, which was asking for you to find the specific heat. You have to rearrange the formula for that problem. The fourth one, she says 2 4s, sorry, it should be a 5. The second one, where it says type 1, says how much heat energy. That's like the first kind. All right, that's like the first one you worked. The last one, sorry for the double 4, the third one, this is a different type of a problem altogether. And I want you to try to figure it out. The hint is you're going to have to pull delta T apart because you're looking for the final temperature. You're looking for the final temperature here. So it's the same thing. You're given your grams, you're given your Q, you're even given the heat capacity of iron. This is in calories per gram. So what you have to do is you have to then take and do the delta T, which is the final minus the initial. So you're going to get your problem, you're going to solve for delta T, then you're going to go through and you're going to actually have to solve for the final temperature. All right, so if you want the answers for these things, you're going to watch the second video I'm creating. It should not take 17 minutes. There's going to be some additional practice problems for you. The answers are at the end, and there's no moving forward without watching the rest of the video. So y'all have a good day today. Sorry I'm not going to be there. Thank you. Bye.